Lesson 9.2 is going to be talking about adding and subtracting rational expressions. And later on we're going to get into the least common multiple of different polynomials. But first we're going to talk about adding and subtracting these rational expressions when we don't have denominators that are the same. So we'll break it down a little more simply and look at just normal fractions. So just numeric values. So if we had 3/4 and 5/7 equals what? So before we can add those together, we always have to make sure that we get those into the same common denominator. Right now we have 4 and 7. Those are not a common denominator. But we know that we can change 3/4 into a common denominator with 7 by multiplying the top and bottom by 7. Same thing with 5/7 here. Multiply the top and bottom by 4. So now we would change it to 21. 7 times 3 is 21. 7 times 4 is 28. So our common denominator is 28. 5 times 4 is 20. 7 times 4 is 28. Now we have that common denominator. So we're able to go right straight through and carry through our normal properties of addition through here. So in adding fractions, the denominator doesn't change. We just carry through the numerator. So we'd be left with 41 over 28, which actually doesn't simplify down, so that's the most simplified version of this fraction that we can find. So that's how to find things numerically using just fractions. Now we're going to look at kind of how do you do this when looking for the least common multiples of different polynomials and monomials. So before we carry it on to rational expressions, let's just see how to find the least common multiple of monomials. There's a couple rules here, and that is that for your variables, always just use the highest power. And for your coefficients, use the prime factorization to find the least common multiples, or use prime factors to find the LCM. Okay, so let's see how that works in this case. If we have this piece, and this piece, let's look at our variables. We have A, B, and C. Well, in one case we have a to the 2, a to the 0 in our second one, and a to the 3. So we're going to use a to the 3. That's our highest power. For our b, we have b to the 1, b to the 5, and b to the 0. So we're going to use b to the 5. And for c, we have c cubed, c squared, and c to the 6. So we'll be using c to the 6th power. So these are going to be our pieces, or our variable parts of the least common denominator. Now we need to look at our coefficients. 15 is one of them. We can break that down into 3 and 5. And that's the smallest prime factorization that we're going to get from that. 16 we can break down into 4 and 4, which each would break down even further to 2 and 2. So our prime factors are 3, 5, 2, 2, 2, 2, which actually we're just going to call the prime factorization of 16 2 to the 4th power. So prime factorization of 15 is 3 times 5. Prime factorization of 16 is 2 to the 4th power. And we need the prime factorization of 20. 20 can be broken down into 5 times 4. Oops. 4 can be broken down into 2 times 2. So we'd say it's 5 times 2 squared. Now, to find the prime factorization of our three numbers, or our least common multiple of our three numbers, should I say, we just add together or piece together all the factors to their highest powers. So it looks like we have a 3 that we need there. We have a 5. found here and here. And in each case, it's only 5 to the first power, so that's all we need. We also have a 2, and the highest power of 2 is over here. It's our 4. So it would be 3 times 5 times 2 to the 4th is going to be our least common multiple of the coefficients. If we solve that out, 3 times 5 is 15, times 2 to the 4 is 16. 15 times 16 is actually going to be 240. So we would say in the end, our least common multiple of these three is 240, the least common multiple of our coefficients, times a cubed, b to the 5th, c to the 6th. So this is the smallest number that those three values can multiply to get into, and they all can go into that. So, looking at the least common multiple of polynomials. What we just looked at was monomials, because each of those was just one term or one factor. Now we're going to look at the least common multiple of polynomials. So, in this case we only have 2, so it's not insanely difficult to look for. Let's just work at factoring each of these pieces out. Remember, we want to just get them all down into their smallest factors. So we can take an x out of this piece. So we have x squared minus x minus 2. Now this piece on the inside we can factor, so we'd say it's x times the factors x plus 1, x minus 2. So these are our three factors of this one over here. Okay, now moving over to this one, we can factor this one down into x minus 2, x minus 2, or x minus 2 squared. It might be easier just to write out both factors right away though. Now we can see our factors are, we have an x plus 1, x minus 2, which we also have the x minus 2 over here. But again, we have it twice here. So it would be like saying x minus 2 squared. So we would write the LCM as x times x plus 1 times x minus 2 squared. Or if you really wanted to, you could write that whole piece out and say x minus 2 times x minus 2. Either way, this is our least common multiple. This is the whole piece here. So this is kind of what we're getting at overall. In general, whenever we have a over c plus b over d, what we're trying to get to is AD plus BC over CD. And you can see where that came from. We multiplied one side by d over d, kind of like before we multiplied our fractions by 7 over 7 and 4 over 4. So this is our 7 over 7, this is our 4 over 4. That would simplify down into something like this, and in the end, this is what we're looking for. So this is kind of the main idea of everything. So let's see how it works. Let's put everything together, and now instead of just looking at the least common multiples, now we're piecing it together in our rational expressions. So if we have 5a squared over 6b plus 9 over 14a squared b squared, we need to find the least common multiple of our denominators, 6b and 14a squared b squared. 6b is going to be 3 times 2 times b. 14 breaks down into 2 times 7 times a squared times b squared. So it looks like our LCM is going to be 3 times 2 times 7 times a squared times b squared. So that's what we're looking for. That's our least common denominator, or our least common multiple, which is now going to be our denominator. So if we were to solve that out, 3 times 2 times 7 actually comes out to 42, a squared b squared. And that's what we're looking for as our, like I said, our common denominator. 42, oops, a squared b squared. So to get our 6b to become 42a squared b squared, we can actually just multiply the whatever we had to get 6b to, which was 7a squared b. So we'll multiply this by 7a squared b as well. Same thing with our 14. To get 14 up to 42 was 3, and then we already have a squared b, so we just multiply this by 3 as well. So 7 times 5 is going to give us 35, a to the 4th b, in between them plus, and then our 9 times 3 is 27. So in the end, this is our simplified version of the rational expressions added up. All right, let's take a look at this one more time. We've got 3x squared over 2y plus 5 over 12xy squared. Look at our LCM of the denominators. We have 2 and y over here. We have 2 times 3, that's 12, times x times y squared. So it looks like our least common multiple, or our least common denominator, is going to be 2 times 3 times x times y squared, which is actually pretty easy because that just stays as 12xy squared. So this piece doesn't need to change at all. We're only looking at the left rational expression over here. To get that one into our 12xy squared, we have to multiply by 6xy and 6xy to change everything. So we're going to write this out as 12xy squared on bottom. 6 times 3 becomes 18. There's already an x squared, so when we times x, it becomes x cubed, and times our y, and still plus 5. So in the end, this is now our simplified expression, our simplified rational expression.